have access to Blackboard. You can bring up the same image that I'm going to project if you wanted to make notes on it or anything like that. I've got extra lab handouts if anybody would like one. It's also on Blackboard, but if anybody would like a hard copy, got a few. Lorenzo, that's the exam. Somebody else has theirs. I have still some handouts from a week and a half ago on precipitation strengthening. I gave those to you during lecture. Oh yeah, go ahead. It's not a technology day. Okay. We'll just do a sketch. So, a phase diagram for steel, iron carbon, a phase diagram will tell us at each of the temperatures we heat treated how much gamma or austenite there was. So had a 0.45, that was the 1045. And we had 1018. And $1,400 was around there, and 1,600 was around there. This is gamma. Don't have to even worry about the other side. And so when any sample was heated to 1,600, it was all gamma. And gamma is the only phase, the only microstructure that transforms to perlite. And perlite was that layers of alpha and Fe3C. So when you heat up, if you aren't making it hot enough to make gamma, it doesn't matter how you cool it down. It's not going to change the gamma. It's not going to change when you quench it. So the first piece of heat treatment of steel So in general, heat treatment has to define a temperature to which you're heating, at what rate of cooling and why. And then sometimes, is there a post-treatment or post-heating? And why? So we talked about precipitation strengthening before we started talking about seals. So the answer to these questions for precipitation strengthening is, this was called solutionize. For age hardening, what's the cooling rate? Quench fast enough enough to avoid any precipitation of theta at the alpha grain boundaries. And then the post-treat for H hardening heat to just warm enough to precipitate theta particles throughout. So that was our first discussion of heat treatment when we talked about H hardening. H hardening is also sometimes called precipitation strengthening. So for heat treatment, it's not enough to say heat it to a certain temperature, and then it doesn't matter how you cool it down. It's not enough to say you're going to heat it to some unknown temperature and then we're going to quench it. You have to, heat treatment is heat treatment if there's a dictated temperature and a dictated cooling rate, and then sometimes also post heat. So for steels, so to what temperature? In that case, hot enough to form all gamma. And that's dependent on percent carbon. So that's this line. This line is the line that defines how warm you have to heat your steel in order to have all gamma. In our case, we did 1600, which is warm enough for both of our steels. If we had a steel that was less than 0.19 or 0.18 weight percent carbon, 1600 might not have been hot enough. We might have had to go even higher. So cooling rate. For steels, the cooling rate depends on which alloying elements are present. We'll use T curves. To predict this. Now, pretty much the fastest quench is a water quench. So we couldn't have quenched any faster than we did, but water quench might not have been necessary in order to get what we wanted for the alloy steel. TTT curves are time, temperature, transition. That's what the TTT stands for. For heat treating steel, we didn't do this, we wouldn't get into this in this class, but for steels, there is a process after you quench fast enough. That's called tempering. And that's heating enough to improve toughness and ductility of martensite. Is that here goal to form martensite? All right, so back to the phase diagram. Hot enough to form all gamma. For your lab, if you had a 4140 or 1045, both of the temperatures you heat treated at are hot enough to form all gamma. But when you're looking at 1018 steel, at 1400, there's some gamma, but not all gamma. This is gamma plus alpha. So 1400 for the lower carbon steel isn't hot enough to make all gamma. So let's talk about these TTT curves. Gosh, I really wish I could project here. So much better than having it sketched. Oh, God.
So
up on the screen. I'll make the screen go down.
What do you need help with? Or try to.
Where? Is it content collection where the folders are? Okay, you know what? I don't want to play this game. So, time temperature transformation diagram. The very simplest one is for 1080 steel. Now the thing about TTT curves is they're not like phase diagrams. They're not maps. TTT curves are meant to predict what microstructures will form under particular cooling rates. All right, so for 1080 steel, the TTT curve looks like this. So when you look at a TTP curve, the first thing I want you to do is, and I can't emphasize this enough, ignore the letters that you'll see on the diagram. There'll be an F, there'll be a C, there'll be an A. Okay, that's the first important thing. All right, so the diagram has that, and then at 400,
Listen.
all right. I don't know how to say this any other way than to say that what these diagrams tell you is what forms as you're cooling, not what's present at a point. So, for example, this, let's say, is our, probably labeled as around 1,500, maybe even 1,400. So 1,400 there. If I have a steel and I'm at, say, around 1,400, and it's 1080 steel, so it's this one. As I'm cooling, can you see I don't form any proeutectoid alpha? I would only form eutectoid. Can you see that? I don't go through this region where I would make alpha. So that makes this 1080 diagram different than any other, and you'll see why in a minute. As I'm cooling, quenching in water gets me to, say, 200 Fahrenheit in about 5 seconds, maybe. So I think our water quench, I'll make that green. I think our water quench is something like this. So let's say that's water. And we get to 200 in about 20 minutes or so, and with air. And this is a log scale. So that's 5 an hour, it's about here. So air cooling does do it within an hour, but not all, this is a log scale again. I would say air cooling is probably something like that. Okay? So I've taken my cooling rates and I've transcribed them over this diagram. Again, this diagram tells me what is formed during cooling. So for water, for the first line is called the perlite start line. It's the point at which perlite starts to form. It's not labeled as such on the diagrams. It's something you would know. And the second line is the, I'll just say no more austenite, no more gamma when I cross that line. All right? This line around 400 is typically labeled M sub S. It's the martensite start. And this line is labeled M90, 90% transformed. Right? The other thing is perlite proeutectoid ferrite or alpha and bainite form via fusion and martensite formation is instantaneous. All right, so I'm water quenching, I cross this line, and I start to form perlite. So before I cross this line, the only thing I have is gamma. So I have gamma, I cool down, I cross that line and start to form perlite. Between that point and this point, I'm forming perlite. Oh, not that one. Yeah, wait. Where's my line? Actually, going right here. From there to there, I'm forming perlite. I never cross the line that says no more gamma. Since I still have gamma, when I cross this line, between there and there, I'm forming martensite. So up until here, I just have gamma. Once it hit that temperature, I started to form perlite. When I hit the martensite start, since I still have gamma, I'm start forming martensite from gamma. Here I'm forming perlite from gamma. There isn't usually a martensite. There's an MS, there might be an M90, there might even be an M95. There's never an MF, a finish making martensite. So if you go back to your notes when I was talking about these different microstructures, perlite, ferrite, bainite, they form when carbon diffuses. They form over time. Martensite forms when the crystal structure literally just fractures into this new structure instantaneously. So martensite forms without any time, instantly. And perlite, bainite, ferrite form with time. So if I had a 1080 steel and I water quenched it, I can expect the best of cases where I get it right into the water, I'll make sure perlite and martensite when I'm finished. If I air cool, then I just have gamma up to this point, and here I'm forming perlite. And when I cross that point, at that point, there's no more gamma. If there's no more gamma, hot enough to have gamma. If there's no more gamma, I'm done with heat treatment. No matter what temperature it is. So those of you that air cooling, I said, after 10, 15 minutes, we can just water quench it. That's because we crossed that point. Even though I entered back in here, it doesn't matter. At this point, there's nothing left to transform. So this is going to have only perlite. Whereas the water quench had perlite and martensite. All right? That's 1080. You didn't use 1080, but that's an important TTT curve because it's the only one where we don't form pro-liquid ferrite. So 1018. So this is still the perlite start. And this is still the no more gamma. It's also sometimes referred to as the perlite finish. Martensite start, martensite 90 are the same. They mean the same thing. But now I have this other new region that I didn't have before, and that is present for every other steel. And that is where proeutectoid ferrite is forming. So this is alpha. Actually, let's just all right, so our water quench, we said, was about 5 seconds. And our air cool, something like that. All right, so this is 1018 steel. So I've got gamma here, and then when I cross this point, I start forming proeutectoid alpha. And from there to there, that's what I'm doing. Still have gamma. At this point, I start forming perlite. And from there to there, I'm forming perlite. When I cross M sub S, then if I still have gamma, which I do, I haven't crossed the gamma, no more gamma line, so from here to here, or from here further, I'm forming martensite. And when I cross M line, M90 line, we can assume there's no more gamma. There's nothing left to happen. So 1018 steel, that's water quenched, as long as it's hot enough, 1600, I'm going to form proeutectoid ferrite, perlite, and martensite. That's what I'll have at the end of the reaction when I get to room temperature. If I do an air cool, I'm forming proeutectic ferrite there. Between here and here, I'm forming perlite. And at this point, there's nothing left to happen. So at this point, it doesn't really matter how I cool. Everything's no more gamma. Transformation is finished. And so what I end up with that heat-treated 1018 is just pro-eutectoid ferrite plus. That's what theory says we should have for the 1018 steels that water quenched and air cooled from 1600. Now, there's 5 seconds. You timed the delay, how long it took for the sample to get from that temperature to the water. And it was a couple seconds. So in reality, this shifts a couple seconds. And maybe we missed the opportunity to be more precise. All right. 10:45.
How do you know how to draw these air and water cooling curves?
Just about how long it takes to get to that temperature.
Okay.
So it's somewhere between 100 seconds is not quite, and this actually probably is even further out. These are in seconds. So if we said 10 minutes, then we mean about 600 seconds. But water quench, I think some people say 10 seconds is a standard, but I think 5 seconds is if we're getting there. If you think about it, once it got in the water and we shook it, 2, 3, 4 seconds to take it out. But it is, this whole diagram is it's not a precision document. Okay, so 10:45. The closest TTT curve that you'll usually be able to find to that is a 1050. So that's a 1050 steel. So if we think about a water quench, and we say it's about 5 seconds. And an air cool. So what do I expect at the end of my heat treatment of the water quench 1045? What should I have? Well, I made ferrite there, and I made pearlite from there to there, and then I made martensite. So this should have proteictoid alpha, pearlite, and martensite. For the air cool, I'm making ferrite in here, I'm making pearlite in there, and then I cross the no more gamma line. Doesn't matter what I do after that. So this one, I'll have proteictoid alpha and pearlite. So 1018 steel, proteictoid alpha and pearlite. 1045 or 50, proteictoid ferrite and pearlite. The same microstructure. However, this steel has more carbon in it. 1050 steel or 1045 steel has more carbon than the 1018 steel. And the hardness, let's say the maximum. The maximum hardness of a steel depends only on the weight percent carbon. So the pearlite in 1018 isn't as hard as the pearlite in 1050. And the ferrite isn't as hard as the ferrite in 1050. So they both have the same microstructures, but we would expect the 1045 in your case to be harder than the 1018, strictly because it has more carbon. If I compare water quench of one to water quench of the other, I see I have, again, the same microstructures. But martensite hardness is dependent on percent carbon. So even if I have martensite here, it's not as hard as that martensite. The maximum hardness of a steel depends only on the percent carbon. The ability to achieve martensite, which is the hardest form of steel, depends on the alloying elements. So 1050, or 1045, and 1018, both of them have a limited ability to make martensite. That's not because of how much carbon they have, that's because they only have carbon. All right, so let's look at 4140, the other one you have. While I'm drawing that, I'd like you to look back in your notes to when I talked about the different microstructures. I talked about ferrite, perlite, martensite, austenite. There was one other microstructure that I talked about that we haven't seen yet. So 4140 is a part of the series of alloys that are the 41 series of alloys. They add chromium and molybdenum. And this is what is created. So this is my making ferrite reagent. And there are, in essence, two of these nodes, these sets of lines. So there isn't an exact line between them, but we could say that there's a curve kind of like that. And then there's another curve. It kind of looks like that, set of lines. All right, so what's the difference? This is perlite start. And this is still no more gamma. So anybody find what that other microstructure was that I listed?
Is it Banite?
Bainite, that's right. So bainite start is this line. And this is all the no more gamma line. So one thing to notice is that I have much more time in here than I had before, right? So my water quench there, and my air cool there. So in the water quench, along there, I'm forming proeutectoid alpha here and there. And then between here and here, I'm forming bainite. And then from there to there, I'm forming marcasite.
Where does it form the ferrite?
So this is the forming ferrite region here. So between here and there.
Is it that same proeutectoid?
Mm-hmm.
Okay.
Yep. So a water quench 4140 is going to give me ferrite, bainite, and martensite. That's proeutectoid ferrite. The air-cooled sample, I'm making we'll use Dectoid ferrite. And then from here to there, I'm forming bainite. I still haven't crossed the no more gamma line, so here I'm forming martensite. Now, you might say, well, where does the perlite end and the bainite start? It's hard to say, and it's possible that there's some perlite with the bainite, but the most of the time is in that lower set of curves. So here, I also have ferrite, bainite, and martensite. I have less martensite than I do here. And I have more ferrite than I did with the other. But I don't have any perlite. I have bainite, which is a harder form of a eutectoid product. Instead of the layers like perlite, it's particles. And then I have this very hard form of steel called martensite. Those are the three that you have in lab. And now you have the tools to talk about what would be predicted based on theory. So, let me get a picture of this, because I don't know if it will look so great this afternoon. The handout that I wasn't able to show you has a number of other steels, different alloys. Before we move on though, questions that we get asked about heat treatability. Where did I write that? Max hardness depends on carbon. The ability to achieve martensite, that is called the harden ability. Hardenability is the ability to make hard martensite, which we get when we add these alloys, alloying elements. It's also sometimes called the depth of hardening. Why would it be called that? Why would hardenability be related to the depth of hardening? I mean, so far, all of your hardness testing really just told you about the characteristics of the surface, the rate at which the surface cooled. But as you go deeper into the surface, it's going to cool slower and slower and slower, right? And so if you have a deep hardening steel, then you can have the harder form of steel to a greater depth. Or you can have the hardness without such a harsh quench. You can get the hardness with air cooling. All right, so two questions to ask. How fast must I quench to achieve all Martin site? And the second, how fast must I quench to achieve any Martin site? Okay, so for the 1018, sorry, the 1080, the eutectoid steel, in order to achieve all martensite, I have to miss this point. So I have to get below about 1,000 degrees Fahrenheit in 1 second. In order to get any martensite, I have to miss that point. I have to get below 1,000 degrees within 5 seconds. All right, so I'll call this question A and question B. So to get all martensite, quench below 1,000 Fahrenheit in less than 1 second. Any martensite quench below about 1,000 Fahrenheit in less than 5 seconds. All martensite with a 1018 steel, not possible. Because this nose is at less than 0 seconds. Any martensite I have to, this is, I'm gonna say it's 10, so probably about 20. Below 1,000 and less than 20 seconds. All right. So 1050. What do I have to achieve in order to get all martensite at 10 on a 1050 steel? just using the models that we've done already.
Less than a second.
That's who? Yeah,
Less than a second.
less than half a second, actually, but yeah, I didn't mark that on there, but. So I have to get below, it's usually about 1,000. How did I write this? Yeah, quench to below 1,000 Fahrenheit in less than half a second. And to get any martensite, right, we do have those on the lab, these same diagrams on the lab handout. To get any martensite, how fast? This is, of course, based on a, sort of my estimate. But, I don't know, close to 5 seconds? And 4140. This has shifted the curves to the right and down. Notice the martensite start temperature is about 400 for 1080. It's about so that's 800, 600 for 1018, 600 for 1050. It's higher here for 4140. So because it's higher, I get to it sooner. Does that make sense? Because this start temperature is higher, I can start to form martensite sooner in the quench. Because the curve is shifted to the right, I have more overall time. So to get all martensite for 4140, I need to quench to below 900 Fahrenheit, and this I think is close to 2 seconds. Actually, it's almost 3 seconds. To get any martensite, this is the point I need to miss. Here. I think that's to the left of that. So that's, I think that would be 300. That point, 100. It's about 200. Below 650 in less than 200 seconds. 200 seconds, that's more than 3 minutes. All right, pardonability. We're still talking about metallurgy in the time of King Arthur. They didn't know why different minerals that they added made their swords harder when they were quenched in the right sacrificial person. Yeah. Yeah. I suppose they thought that was part of the sacrifice, the magic of it. It's actually because human temperature blood is the perfect cooling rate for steel. Not giving anybody any ideas. But we're still talking that. We're still not talking about really the common era as far as technology and making steels better. As a matter of fact, there is a characteristic of steels that's called the ductile to brittle transition. Where did you write that? I really don't want to erase anything here, so I'm going to go here. The ductile brittle transition temperature. This is a temperature, and it's unique to each different chemical composition. The ductile to brittle transition temperature, whatever it is, if you get below that with your steel, it begins to act like glass. It shatters. It has no ductility. And it turns out that the things that we add to make steel hardenable raise that temperature. Raise that ductile to brittle temperature. So plain carbon steels, the ductile to brittle transition is way, way below freezing, like probably below -50 Fahrenheit. A temperature that steel would not see in use. But the ductile to brittle transition temperature for some alloy steels is above freezing. So we had this big group of ships. What do you call a ship in battle? The kinds of ships that are used in battle. Can't think of it. What was that?
Warships.
Well, okay. Anyway, right around World War I, maybe a little after, there are a bunch of ships that were in port, just sitting there. They have been made from an alloy steel so that they are harder. Makes sense. The temperature dropped in the seawater to below the ductile to brittle transition temperature. And they all cracked in half without anything striking them, without any munitions of any sort, just a little tap. They were under enough stress that they literally, the hull cracked in half all the way down the row. And that's when we kind of started learning about the ductile to brittle transition temperature, and that's much more recent. All right. I think that's it. All I want to talk about beyond this is polymers, and that'll be a week from today. So what do we have next? Friday, this opportunity makeup test, hour and a half. We'll start at 10:45. I'll try to be here at 10:30 if there are questions. Can't have a review session, sorry, I don't have time. And it covers everything in the class up until now. All right? Now, obviously, I can't put everything on the test, and if you're trying to pick which kinds of things might be on this test, don't think about the things that were pretty easy on the exams. Just look at the exams. If it's not on an exam, if that kind of problem isn't on an exam, it isn't on this test. It's not going to be the same problem, but the same topics. All right? Homework 7 will be using the other TTT curves to do exactly the same thing that we just did. Michael,
If we don't plan on taking that exam, do we have to?
you don't have to come. So we've got homework 7 due at the final exam. We've got the lab report due at the final exam. How would you feel about not having a final exam? I mean, I can pretty much do whatever I want. Yeah? I would still really like it if you come on next Tuesday, just to, so we can chat about polymers. But I would also like it if you did well on all of your tests. And I think that homework 7 and homework 6 will show me that you understand the material that I would put on the final. Don't advertise this, okay? I mean, you can say, oh, Sullivan, she's the best professor I've ever had. You can advertise that. But yeah, when people are jealous, they don't think well, right? So let's not make other people envious of the change in plan, all right? I appreciate you being here, and not everybody's here. Before you leave, I'm gonna have a sign-up sheet for the test on Friday. You can sign up. And if you know of somebody who wants to take the test on Friday and isn't here, tell them they need to email me, okay? Thank you. We'll see some of you in a week. We'll see some of you on Friday.